Welcome to Lecture 11 of Modeling and Simulation of Physical Systems, in which I shall cover techniques to model the fluid systems. In mechatronics engineering, the fluid systems-based actuator utilize the fluid mechanics and its properties to generate mechanical motion. And they find lots of application in industrial, automotive, and aerospace industries. Let's take an example of a simple hydraulic press in which our goal is to lift a car upward by applying some input force on the left hand side over here. As a result of this force, we are going to try to compress an incompressible fluid, which what this means is that the pressure P1, which is on this side of the hydraulic press, will be translated directly into the pressure P2, which is the same as the input pressure on the other side of the hydraulic press. As a consequence of the conservation of the pressure, we have a relationship between the corresponding forces. So let F1 is the force applied on the input side and F2 is the force generated on the output. Then P1 equals to P2 simply asserts that F1 over A1 equals F2 over A2, which means the ratio of F1 to F2 is the same as the ratio of the areas on the input and the output side, respectively. And if we can tweak these areas such that A1, that is the area at the input side, is much smaller, A1, the cross-sectional area over here, is much smaller than the cross-section area over here, which is much larger, then F2 can be made much higher than F1. And this is the principle of force amplification in a hydraulic system. Some typical examples of fluid system actuation include the pneumatic position servo and the hydromechanical position servos. In both cases, we are interested in controlling a precise position of a load M over here and over here. The load M is experiencing some opposing or disturbance force FL. In case of pneumatic position servo, we are going to utilize air and its properties such as compressibility to actuate our system. In case of hydromechanical position servo, we are going to utilize the properties of some liquid as a fluid by means of actuation. These are the examples given in the textbook figure 7.4 and 7.5 that I intend to cover in more detail in the next lecture. The main advantage of the fluid system is their higher force or power density. So we say that the fluid-based actuators are helpful wherever we need very large force applied to a very small volume or small area. That gives them an advantage over conventional actuation systems which are primarily electromechanical in nature, such as electrical motor. Other advantages of the fluid system-based actuation include the improved heat dissipation, and that's because when a fluid moves inside the system, it eventually in turn moves the actuator, and because the fluid is itself moving, it is carrying the heat from one part to another. In fact, the heat is being circulated and essentially homogenized. Therefore, we don't run into the situation of hotspots. That temperature can be distributed easily and uniformly across the system, and in most cases the heat is brought back to the reservoir from where it can be easily dissipated. The other advantage of the hydraulic and the pneumatic systems is that of a higher bandwidth. In simple words, a system with higher bandwidth is a system which responds faster to the input, that is, a more responsive system. It is a lot easier to quickly set a fluid system into motion, and that's because the system is based on fluid. And fluid motion can in turn be translated into the actuator motion by means of the rate of change of pressure. So the two the two advantages, heat dissipation and higher bandwidth, make them an interesting choice for range of industrial application based upon the fluid actuators. At the same time, there are some demerits of the fluid-based systems. One of them being that it is difficult to control the systems, so the controllability becomes an issue. The other overhead is that we need a separate fluid reservoir in most cases, which often requires maintenance, periodic maintenance and upkeep. And the weight of an overall system increases partly because we need to include the weight of the reservoir and all the accessories to transmit the fluid. And the final thing is the difficulty to model the fluid systems. These systems tends to be a lot more nonlinear compared to their electromechanical counterparts. Hence, modeling a fluid system is difficult compared to the modeling of the electromechanical systems. In this lecture, I'm going to describe some important properties of the fluid-based actuation systems, the first of them being the fluid capacitance. Fluid capacitance is a property that allows the storage or the release of fluid energy by changing the fluid pressure over time. Essentially, it relates the fluid flow rate, capital Q, with the rate of change of pressure, where capital P is the fluid pressure. A common real-life example is when we try to inflate a balloon. Initially, when the flow rate, when the balloon is empty and we are trying to pump air to inflate the balloon, the pressure inside the balloon is changing fast. So this quantity dP over dt is high. And that's high because the fluid, might be air or gas, is rapidly flowing into the balloon. So this Q is also high. But with the passage of time, as the volume of the balloon gets larger and larger and larger, we see that at some point the flow rate, that is the rate at which the air or the gas is entering the balloon, decreases at some later stage. And that's because the pressure inside the balloon the rate of change of pressure inside the balloon begins to decrease. That's because the pressure inside the balloon remains more or less fixed at this point. So that is a very good example of the fluid capacitance. To understand fluid capacitance mathematically, we're going to consider a situation where we have a region through which the fluid is passing. That region has some volume and it is described as a control volume. The fluid can be considered flowing either left to right or right to left, whichever you think or you find more convenient to understand is fine. So suppose that the fluid is flowing left to right. Then the portion of the fluid that is left to the control volume has some density ρ1 and it has some flow rate Q1 over here, this region. And the density of the fluid on the other side of the control volume is ρ2 and the flow rate Q2, that's over here. And inside the control volume, we have taken density ρCV and the volume as VCV. To derive the expression of capacitance, we're going to utilize the continuity equation, which says that the rate of change of fluid mass inside the control volume, that is, if we are interested in knowing how quickly the mass is changing over here, the mass of the fluid changes over here, and at what rate, that rate of change of mass is just the difference of rate of incoming fluid mass and the rate of outgoing fluid mass. So the rate at which the fluid mass is flowing into the control volume and the rate at which the mass is leaving the control volume. And the difference of the two is the rate of change of mass inside the control volume. It is fairly easy to understand. Then we can write down the rate of change of mass as the derivative d over dt mCv, where mCv is the mass of the fluid inside the control volume. That is equal to rho 1 times Q1 minus rho 2 times Q2. So remember, rho represents the density of the fluid and Q represents the flow rate. So essentially this equation, this form of the continuity equation, is allowing us to relate the rate of change of mass with the help of with the flow rates. Now we can express mass as a product of density and the volume, and that will be the density of the fluid inside the control volume and the volume of the fluid inside the control volume as VCV. So the left hand side has been written as a product, a derivative of the product. If we simplify this model or the system with an assumption that the density of the fluid remains the same throughout the system, that is, the fluid inside or outside, or the fluid at the inside the control volume, on the inlet, might that be rho 1, or the outlet, rho 2, all the fluid density is constant throughout, that is rho. And so that's one assumption. The other assumption, well, that's the other assumption is not actually an assumption. It's just the different it's a simplification of the variable name. So VCV is just taken as V. So then our above expression will be simplified as follows. So the rate of change of density times volume is equal to rho times Q net, where Q net is the difference of the flow rates, Q1 minus Q2. And we finally have an expression after taking the derivative on the left hand side. Rho V dot plus V rho dot is equals to rho times Q net. So this gives us a simplified form of the continuity equation, where the simplification comes about after taking this assumption that the density of the fluid remains constant throughout the system. Once we have this expression, we would now like to focus on one of the terms on the left hand side, which has a derivative of the density, that is rho dot, which essentially says that the density of the fluid is changing over time. That is the rate of change of the density. Right? And remember, when we said in the last slide that the density of the fluid remains same throughout the system, that was that is when we said that the density remains fixed in the space, not in time. So here we're saying that if we have a term rho dot, that means the density is changing with time. So we need to express rho dot in terms of an important property of the fluid that represents the rate of change of the density. That's where we need to think about the compressibility of the fluid. Because if the density is changing, that means that that essentially points to the fact that the fluid under consideration is either being compressed or released, uncompressed essentially. So we introduced the bulk modulus over here, which is defined as beta equals to, so beta over here is a bulk modulus, that's rho times the rate of change of pressure with reference to the change in the density at a given pressure and a temperature. So remember, it is defined at a given pressure and the temperature, and we're going to eliminate rho dot by substituting it by representing it in the form of the beta and the pressure rate of change of pressure. All right, so first we need to express rho dot by using a chain rule. So the rate of change of density, that's time rate of change of density, is essentially the change of density with respect to the pressure and then the rate of change of pressure. So by means of chain rule, we can express rho dot as partial rho divided by partial p and the partial p divided by partial t. So as a consequence, we have a p dot term over here, and the rate of change um, of what we are going to do over here is that we're going to bring this term on the left hand side after taking its inverse. So we are going to get 1 over rho prime rho dot, which is the term originally on the left hand side, it's in the denominator, times the rate of change of pressure. So eventually we're going to get this expression that relates the rate of change of pressure with respect to the rate of change of density, which is simply the inverse of this guy over here. And we're going to substitute that in this equation. And we're going to get beta equals to rho times the rate of change of pressure divided by rho dot. Then our continuity equation becomes rho times b dot plus v times this guy over here, that is rho times p dot divided by beta, and that is rho times q net. In fact, what we have done over here is that we have replaced rho dot with this term over here by utilizing the expression of the bulk modulus. After cancelling out rho from this equation, we finally arrive at an expression where we have the rate of change of volumes plus volume divided by bulk modulus times the rate of change of pressure equals to the net flow, the net fluid flow rate. So remember over here, the P is the fluid pressure inside the control volume. Sometimes this pressure is used as it is, or it may be used in the form of pressure difference, where the pressure inside the control volume is taken as the difference of the pressure on the for example, the pressure of the fluid that is flowing into the control volume and the pressure that the fluid experiencing on the other side, on the outlet of the control volume. So if the control volume has fixed volume, then the volume is not changing in time, that's v dot equals to 0. Therefore, the net flow rate is simply volume divided by beta times p dot. So this simplified expression is helpful in understanding the fluid capacitance. That's because volume divided by bulk modulus is defining the fluid capacitance by relating the rate of change of pressure, that is P dot, with the flow rate, which is very analogous to the capacitance we're familiar with, the capacitance in the electrical circuits, where the current is equal to capacitance times the rate of change of volume. So in this analogy, the pressure will map to the voltage and the flow rate will map to the current in the electrical circuits. Let us consider an example of a fluid capacitance which will be helpful to model more complicated fluid-based actuation systems. It is an example of a spring-loaded piston capacitor. What we have over here is a piston which is loaded by a spring, and both the spring and the piston are enclosed in a cylindrical housing. To actuate this system, we're going to pump some fluid, for example air, with a flow rate Q, and it is going to develop some pressure in this section. That's the pressure PCV. The pressure of the fluid on the other side, which is essentially connecting which is actually the same as the open air pressure. That's atmospheric pressure, PATM. And naturally, if you want to move this piston to the right hand side, we want this PCV to be higher than PATM. So by changing this pressure, PCV, we can control the motion of the spring-loaded piston. So for the formal modeling procedure, we're going to assign a displacement variable x to the piston, and this piston is modeled as a rigid body. So whatever displacement is experienced over here, the same is the displacement experienced on the other end. So the displacement variable remains the same, that is x. And the initial position, or in other words, the lower dead end is at x naught. So the displacement the distance from the left hand side of the cylinder to this point over here is x naught. The cross section area of the cylinder is capital A. Our main tool is the baseline fluid capacitance model expression, which says that the flow rate is equal to the rate of change of volume plus volume divided by bulk modulus times the rate of change of pressure. So this is the baseline expression we are going to use, and we're not going to drop this term as it is because the volume might be changing with time. So general expression has been used, and remember to always start with this expression. Then further assumption before writing down the expression of the capacitance is that the spring and the pistons are considered to have zero mass, or their masses are negligibly small. But we are going to assume that the spring does have some stiffness represented by a spring constant K. Our job then is to find out an expression of the fluid capacitance by relating Q with the rate of change of the pressure difference. So remember, in this case, when talking about the pressure difference, which is essentially PCV minus PATM, the difference of the two pressures. In our modeling technique, we are going to split this problem into two parts. The first of them is to write down the modeling equation for the mechanical subsystem, which is actually not that complicated. It contains a piston part and it contains spring. And as we know that although the piston may experience some force or forces due to these pressures, PCV or P atmospheric ATM, it will have zero dynamics just because it has zero mass or zero inertia. Then the only thing we need to care about is the spring. So the displacement of the spring needs to be taken into consideration. We know that the left end of the spring is mounted on the piston, so the displacement of the spring will be same as the displacement of the piston left end of the left side. That is the displacement x. The other end of the spring is fixed, unlike that of the piston. So remember, the piston right end, the right terminal, can move outside the cylinder back and forth, but the spring will remain confined to the boundaries of the cylinder. So the right hand side boundary of the cylinder is going to confine the displacement of the spring. In fact, the displacement over here is just zero. And if we consider the force acting on the spring due to the pressure, there's a pressure PCV and PATM. We know that there's going to be some force applied on the spring. If we take this force acting rightward on the left terminal, call this force FCV. It is a net force due to the net pressure difference. We say that FCV is a force due to the net pressure difference, that is PCV minus PATM. Then it is easy to write down the expression that relates FCV with the displacement. So that expression is simply FCV equals to Kx. It is going to be our first equation, and that completes the modeling of the mechanical subsystem. We now move to modeling the fluidic part of the system, the fluid subsystem. And in this case, we are going to first relate the force with the pressure. So FCV, as we discussed before, was due to the pressure difference, but formally we should be writing it as expression and say that FCV equals to area times the pressure difference, where A is the cross-section area of the cylinder. And we're going to substitute that in the equation 1 in the previous slide, and we're going to get A times delta P equals to Kx, where again delta P is the difference of PCV and ATM. Taking a time derivative of this expression is going to give us the rate of change of area times the change in pressure equals to the rate of change of K times X. And obviously in both of these time derivatives, there are going to be some constant terms such as K and A. So after taking the derivative or computing the derivative, we are left with A times delta P dot equals to K times X dot. That's because the pressure and the displacement are the only two time dependent variables in this equation. That is our equation number 2. All right. Now, what we are, so the reason why we are taking time derivative is because we are going to utilize this expression and somehow resolve this V dot term in our capacitance equation. So how to resolve this V dot term? Well, first of all, write down the V. V is the volume of the fluid. So essentially we are talking about the fluid over here. This is our control volume, this volume, and therefore this V is basically A times it is a cylindrical part, so the volume of the cylinder is the cross-section area times the height, which is the displacement in this case. So as this piston moves forward by displacement x, the volume will be increased to this point. So depending upon the value of x, the volume is going to change. So the height essentially is this thing. The height, effective height of the cylinder is x plus x naught, and the area is A. So with this volume expression, if you take a time derivative of the volume, you're going to get A times x dot. That's because this guy x naught is fixed. So we are going to get V dot equals to A times x dot. Equation 3. Our job now is to eliminate x dot from 2 and 3. Because right now, although we're trying to resolve this V dot expression, but in doing so, we have introduced another derivative, time derivative, that is x dot. So we want to get rid of x dot over here. And that can be done by eliminating x dot if we solve equation 2 and 3 simultaneously. And this is going to give us an expression in terms of V dot equals to A square delta P dot divided by K. And this term contains delta P dot. So our objective was to eliminate the x dot and to introduce P dot term over here, so that we already have a P dot term over here. We want P dot term over here as well. And those P dot or delta P dot terms can be taken as a common, which is, and then can be separated out as a common factor. That is the main objective. Therefore, the final equation, one thing we need to make sure is that the fluid equation that to be used over here has delta P. Therefore, our baseline equation is this. And we have an expression by substituting V dot with A squared delta P dot divided by K. This is substituted over here. The other part remains same. And the final expression is very interesting because we can relate Q with delta P dot that is multiplied by some constant or hopefully constant expression it is easy to see a coefficient of delta P dot. In this case, the coefficient of delta P dot is a square over k plus v over beta. So the fluid capacitance in this case, we can say that this is essentially a square over k and volume divided by beta. That is the requisite, that is a desired fluid capacitance expression. So here it is, the fluid capacitance expression has been obtained. The question is it really constant? We know that the area is constant, the spring stiffness is constant, the bulk modulus, and the volume. So there's a question mark over here. In most cases, when we talk about modeling the fluid-based actuator systems, it happens very often that either volume or bulk modulus of the fluid may not be taken, are not constant in reality. So there are some simplification, or there are some simplification assumption that needs to be that are usually made, such as if we assume that the volume is not changing a lot, then V is taken as some constant value or some mean value. But in general, as you can already see that this is not going to be the case in general. So this is a time varying quantity. So volume divided by bulk modulus is time dependent. It's not constant. And therefore, we're going to multiply a time dependent quantity with another time dependent quantity, that is the rate of change of pressure. Therefore, the above system is non-linear. It is something you can prove by the first principles of signal and systems, as we discussed in second lecture. And this is also your homework, in which you are going to show that the system is non-linear in another scenario in which the displacement is large. All right, now comes the fluid inductance. Fluid inductance is a property that defines the inertia of the moving fluid. In simple words, we say that fluid inductance describe how much the ability of the fluid to oppose the change in its flow rate. When you try to change its flow rate by means of applying external pressure, the fluid is going to resist, and that property is described as the fluid inductance. So how we're going to derive its mathematical expression? Well, let's consider another scenario. Again, we have a section in which the fluid is flowing, call it control volume. And we're going to focus on this control volume most of the times, as this was the case for the fluid capacitance. Let's say we are trying to exert some pressure on the fluid from the left and the right hand side. The pressure over here is P1, left hand side. The pressure on the right hand side is P2. And the corresponding cross-sectional areas are A1 and A2. Actually, they are already shown. Then, to derive the expression of fluid inductance, we need to define the mass of the fluid inside the control volume, that is M. And later on, we shall also describe the density. It's not mentioned over here on this slide. Nevertheless, the velocity of the fluid inside the control volume is V and small v. And the fluid momentum then becomes M times V. Then, if we want to relate the force, the net force acting on the fluid, that is P1A1 times P2A2. That is this force, call this F1, and this force F2. So the difference of the two forces, the net force F applied to the fluid, and that force arises due to the external pressure P1 and P2 applied on the fluid inside the control volume. And we know that the force can be related with the rate of change of momentum. In fact, the force is equal to the rate of change of momentum. So F equals to d over dt mv, which becomes m dot v plus mv dot. Then we're going to make some assumptions further. The fluid mass and the density inside the control volume, they remain unchanged. This is a very important assumption. Essentially, we are saying that the rate of change of mass inside the control volume is 0, which was not the case in case when we were trying to derive the expression for the capacitance. We also assume that the two cross-sectional areas on the left and the right-hand side of the fluid, they are the same, equals to A. And lastly, the length of the control volume is taken as small l. Then our job to derive the expression for the fluid inductance is to relate the fluid flow rate, capital Q, when the pressure delta P is applied, where delta P is the difference of P1 and P2, shown here. So the first equation will be the force times force to relate. So remember, our previous expression was F is equal to mv dot plus m dot times v, and we said that m dot equals to 0, so that term is equal to 0, and the remaining expression will be like the force equals to mv dot, and the force is further resolved as the area times the difference of pressure. The left hand side is essentially representing a force, and we're now going to further expand and say that we wish to relate the pressure with the rate of change of its flow rate. So we need to introduce Q. For that, Q equals to area times the velocity. So that's the flow rate definition. And then if you take the derivative of the flow rate, we're going to get area times the velocity derivative, or velocity derivative equals to the rate of change of flow rate divided by A. So by that, we have now introduced the rate of change of flow rate. We have now an opportunity to plug this V dot into this expression and express that in the form of the rate of change of flow rate. But we also have this mass in equation 1, so that is just rho times the density, which is the density of the fluid, times the volume, which is again related, split into the product of area times the length. So when we substitute mass and the rate of change of velocity into 1, our final expression gives us it is going to relate the rate of change of flow rate, that is Q dot over here, with the pressure difference, and the coefficient of the flow rate is rho L over A, and that is the fluid inductance. And you can draw an analogy with the electrical inductance, where we said that the voltage was, remember, so this V over here, you have to be careful over here with the variables. So voltage equals to inductance L. Remember, electrical inductance, we used L. We also use L for the fluid inductance. So L times the rate of change of current. So the rate of change of current. So again, flow rate is going to map to the current. So current is very similar to the flow rate. It's just that it's a flow of charges, not the fluid. And the pressure or pressure difference maps to the voltage. So that concludes our description of fluid inductance. The last property we are going to discuss is the fluid resistance. It effectively describes some kind of a pressure loss, and that occurs when the fluid is flowing, and as a result of its flow, it is going to lose some of its energy, so it's going to dissipate some power, and that power is often reflected as the drop in its pressure. Essentially, we are trying to relate the flow rate once again with the pressure difference, but here we are trying to have a proportionality relationship rather than the rate of change of either flow rate or the pressure difference. But this proportionality is often difficult to achieve, as we know that in case of electrical circuits, so I is proportional to the voltage drop across the resistance. So it's the same concept, although in case of fluid system, this exact this proportionality is difficult to achieve unless we enforce certain um, properties in the flow of the fluid, such as the laminar flow, a smooth flow that occurs at a low flow rate or at a low pressure drop. So if those assumptions are true, that the flow rate is low enough and the pressure drop is also low enough, then we do have a fluid resistance in which the flow rate is proportional to the pressure difference. So that equation may be true only in case of laminar flow. In other cases, however, such as the orifice flow and compressible flow, those assumptions are not strictly true. And in those cases, in the first case, in case of orifice flow, the Q is actually proportional to the square root of pressure difference with some sign restrictions over here. And the expression for the compressible flow is rather more complex. It's omitted for the sake of simplicity and brevity of our discussion. Those things I hope will be covered in the other course the students are taking this semester. That is the course of hydraulics and pneumatics. All right, so with that, I would like to conclude my lecture on the basic modeling principles of the fluid systems, where we have looked at some very basic properties, and we have restricted ourselves to only those properties which will be used to model more complex systems in which the fluid is used for the actuation. I hope you enjoyed this lecture, and I'm sure you will have some questions, and for that we're going to have our regular Q&A session on Thursday afternoon starting at 2 p.m. Till then, stay safe and have a nice day. Thank you.